Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 23, and in this lecture we will be working more towards the intrinsic carrier concentration and their change when we move from room temperature to cryogenic temperature. So the outline of the talk will be we will be looking into the intrinsic carrier concentration, and then we will try to develop a basic relationship between the intrinsic carrier concentration Ni and the band gap Eg. We will just go through the basic properties of cryogenic fluids which we get, and then look into the cryostat experimental setup at the later stage. So, why this lecture is important is you need to appreciate the point that intrinsic carrier concentration plays a major role in determining the output electrical characteristics of a device. Now, if the carrier concentration itself falls down to a very low value because of low temperature, then the driving capability get compromised for the device, and that is the reason we need to very appropriately study how does intrinsic carrier concentration change and what is its relationship with respect to the ambient temperature. So, let us go through this intrinsic carrier concentration graph. I will keep it to the very basic, and then we will see how it works out. Now, typically when you try to find out an intrinsic carrier concentration, you multiply the probability of finding the electron at a particular state, energy state, and then you multiply with the number of states per unit volume, right. So, energy density. So, that is the reason you see that I have done what I have done. This is my Fermi Dirac expression, and this is my GC, or basically the number of states per unit energy states per unit volume, right. So, if you multiply these two, I get the total number of electrons carrier concentration. It is something like this. So, I have say number of classes available, right. There are number of classrooms available. Now, if you know how the classrooms are distributed in a school or in a college, and you also know what is the probability that a particular classroom will be occupied by certain number of people, if you multiply these two, you get the total number of students who are there in the school or a college. Exactly same thing happens in a semiconductor. So, the Fermi Dirac principle which you see on the left hand side, which is this one, is basically tells me that f of E, the probability of finding an electron at energy state E, is given by 1 upon 1 plus e to the power E minus Ef by kT, where Ef is basically my Fermi energy. This is my Fermi energy, right. Now, interestingly, if you look very carefully if you look at E equals to Ef, right, this e to the power 0, and therefore, f of E becomes equals to 1 by 2, right, because this becomes equals to 1, and then I get a 1 upon 1 plus 1 is equals to 1 by 2, which tells me that the probability of finding an electron at exactly the Fermi level is half. And any state, if you go this side, right, and if you come this side, let me come to low temperature 4.2 Kelvin, which is very near to absolute 0, is the blue curve which you see here, right, the blue curve. This one is the blue curve. This green curve is at 77 Kelvin, and this red curve is at room temperature, which is 300 Kelvin. So, this is basically at 300 Kelvin. What does it state is, that if you at 4.2 Kelvin, if you look, then the probability of finding the electron below the Fermi level is 0, right, which is this one. So, the blue curve actually touches this axis, and this is 0 axis, 0 probability, and above Fermi level it is 1, right. So, it is more of a step function which you see for a 4.2 Kelvin, right. This is 0 probability and this is 1 probability. This is at 4.2 Kelvin, which means that at 4.2 Kelvin, Fermi level is a differentiating point which tell me that all the states above Fermi level are fully filled up, and therefore, the probability is 1. All the states below Fermi level are fully empty, and the probability is 0 in such a case, right. Now, let us see what will happen if I slightly increase the temperature from 4.2 Kelvin to approximately 77 Kelvin or 80 Kelvin, whatever. Now, what happens therefore is, since you have increased the temperature, some of the electrons which were fully filled up below the Fermi level will now get moved up, because you have given some energy. So, if there is a state available, and if the electrons are available here, all the electrons were occupied here at almost 0 Kelvin. Now, if you start increasing the temperature, some of the electrons will gain thermal energy and they will be crossing this barrier and reach to the higher state, and therefore, there is a probability of finding electrons even above the Fermi level. And that is the reason you see the green curve. If you look here, you see there is a finite probability even here. It is not 0, right? It is some non-zero value which you see here. Now, since obviously you are not adding electrons from external source, the electrons have moved from a lower state to the energies above Fermi level. So, the probability of finding electron, if it is x at above Fermi level, it will be minus x at, that is the reason you see the green curve is perfectly symmetrical. Not only green curve, the red curve is also perfectly symmetrical, which means that the electrons from a lower energy states have been advanced to higher energy states. So, the lower states are empty, and that is the reason the probability falls down, and the higher state starts to get filled up, and therefore, the probability increases from 0. So, that is the whole thing about Fermi-Dirac principle here. So, we have learned two things from here, that at Fermi level is a critical level where you will have all sorts of transition in terms of probability of finding an electron, and Fermi level is a point where the probability is exactly half of finding the electron, right. And above Fermi level your the states are fully empty, below they are fully filled. Now, let us concentrate on the second curve, which is this one, right. This shows you the variation of state with respect to GE as a function of GC is the states, number of states. So, if you look at the formula here, this tells me that this is almost constant, right, and therefore, GC of E, number of energy states per unit volume, is proportional to root of E minus EC. So, my G of C E is proportional to root of E minus EC, right. If you look very carefully, since it is a parabolic form, all the states which you see here is a parabolic in nature. So, the number of state goes on increasing as E crosses EC. EC is a conduction band edge. If you remember your basic devices courses, this is my EC, this is EV, and I have an energy state here E, right. Higher the energy state or further away this energy state away from EC, more will be the states available. So, the number of state parabolically grows as your energy level exceeds the conduction band edge and moves higher and higher. So, very near to the conduction band edge, the number of energy states available will be per unit volume will be relatively small. But as you start moving higher and higher in energy state, the number of states goes on increasing. That is what I wanted to show here in this case. Which means therefore, if you multiply the Fermi level with that of the GC of E, the profile which you get is basically on the right hand side here. Let us first look at room temperature, because that is relatively easy to sort of explain, and then we can come to the 4.2 Kelvin case. When you multiply the first Fermi-Dirac function with that of GC of E, you get a curve which is on the left hand side, right. And if you look at the room temperature, if you plot the number of carriers with respect to the energy level, you will see that it is near the conduction band edge, right. This is ECRT, which is the conduction band edge at room temperature. Almost the carrier concentration becomes very large here, and then it starts to decrease and then becomes higher and higher as you move up. This is quite interesting, which means that the number of charge carriers which you will have near the conduction band edge will be small. But one thing to care about is as you move up in the energy level, the number of energy states, since the density goes on increasing, and if the probability is fixed, the number of electrons available there are relatively large. But let us see what happens when you go to 77 K, and that is what is critical is all about. At 77 K, so you see your intrinsic carrier concentration is 10 to the power 10 per centimeter cube, let us suppose. You know, in room temperature it is 10 to the power 15 to 16 per meter cube, which is 10 to the power 10 per centimeter cube. And this is at 300 Kelvin, this is a fixed value which has been set. However, let us come to 77 K and 4.2 K. What we end up is, so how do you find out the carrier concentration? The area under this curve is basically my carrier concentration. So, this if you look very carefully at 77 K, this area is relatively very small, and therefore, Ni is relatively very small. It is, in fact, it is of the order of 10 to the power minus 20, right. It is 10 to the power minus 20, whereas it was 10 to the power 10 in case of room temperature. it is 10 to the power minus 20 at low temperature. And if you further go down at 4.2 Kelvin, you see it's almost a straight line, there is no area available, and the Ni or intrinsic carrier concentration is 10 to the power minus 678 per centimeter cube, right. So, what I wanted to show from this, take away from this presentation slide, is that as the temperature goes on reducing, your intrinsic carrier concentration also goes on reducing, and that is primarily because at low temperature the Fermi-Dirac function is almost like a square function, and therefore the probability of finding is 0 or near 0, and that is the reason the number of intrinsic carrier concentrations are very small. So, this is your Ni which I am trying to find out, right, intrinsic carrier concentration here, correct. So, this gives me a brief picture about how the intrinsic carrier concentration varies with respect to this thing, and this is an experimental data which we have found out, and just to showcase what I was discussing there theoretically can also be thus, and you can find it from this book. This is a good source for those researchers trying to start their research or in the midst of their research on cryogenics. This book by Corclays and Edmondo and Jamaldin is a standard book, is a good book to follow initially. Now, if you try to plot the intrinsic carrier concentration with respect to temperature, so this is the temperature here and this is the intrinsic carrier concentration. As you can see, at 300 Kelvin, if you plot, the intrinsic carrier concentration may be quite large, right, and in fact it becomes very, very large. Even at 400 Kelvin it becomes more large because more carriers are available to contribute. But the most interesting point is as you shift towards this scale, very low temperature, less than 50 Kelvin, you see it has fallen down to a bare minimum, and that is what the problem of cryogenic electronics is all about. Your intrinsic carrier concentration falls down drastically. Now, let us develop a relationship between the intrinsic carrier concentration and the band gap, because till now, if you go back to even to your previous slides, if you look here, the conduction band edge also seems to change when your temperature changes, right. So, your band gap is actually, if not very drastically, is actually a function of the absolute temperature, correct. So, you need to be very cautious on two fronts, that not only the intrinsic carrier concentration is coming down, but the band gaps also seems to change, right. And when that changes, the probability of electron finding in the conduction band also changes. So, this is a complicated mixture of two things. One is the intrinsic carrier concentration and another is the band gap energy which we see. So, let us try to find out the relationship between the intrinsic carrier concentration and the band gap. Now, the Fermi energy level for the intrinsic semiconductor is called the intrinsic Fermi level. If I take an intrinsic semiconductor, right, what is an intrinsic semiconductor? Which has got no excess carriers available to it, right. You have, let us suppose I am an intrinsic semiconductor, then my Fermi level is almost in the middle of the band gap, and I say that to be as the intrinsic Fermi level, right. Why in the middle? Because equal probability of finding an electron and hole at the below is intrinsic Fermi level. Now, the intrinsic carrier concentration, I am not going to derive these equations, but these are available in standard semiconductor device books. So, I will not go into details of that. I will just give you a small insight. The insight is that my N0 is given by this. N0 is the number of free electrons available and is the number of free holes available, right. Interestingly, more is the conduction band separated from Fermi energy level, right. From further the distance is, lower the concentration of N0, which is acceptable also. Now, which means that if your conduction band edge is further away from the intrinsic Fermi level, then EC minus EFI becomes large, and since it is a negative exponent, my N0 falls down exponentially, which means that even if you shift your intrinsic Fermi level slightly away from the conduction band, that affects the total free charge carrier concentration in the conduction band. Same thing happens for the hole in the valence band. If you shift the difference between EFI and EV to be slightly larger, you end up utilizing a larger value of or smaller value of P0. So, your N0 is exponentially dependent on EC minus EFI in exponential sense, and this is quite interesting, that which means that even a small difference will give rise to a large change in the number of carriers, both for electrons as well as for holes. Okay. So, if we take the product of the previous two equations, means this we multiply right? We multiply this, then we multiply P0 with N0. Now P0, N0 equals to Ni, intrinsic carrier concentration, and P0 is also equals to Pi, right? So if you multiply both of them, I will get N0 P0, and on the right hand side get Ni square Pi square. So I get Ni square equals to Nc Nv, Nc times Nv exponential, exponential minus Ec minus EFi by kT, right, into exponential minus EFi minus EV by kT. You will ask me what is NCNV? NCNV is basically the density of states, right? So basically it tells me how many number of states are available per unit energy, per unit volume in a conduction band and the valence band. In the conduction band it is given by Nc, in the valence band it is given by Nv. Now in this case, if you look, and then if I do this like if I change it, I get Ni square equals to NCNV exponential minus Ec minus Ev. Why? Because EFi will get cancelled out from here. This is minus EFi, this is plus EFi, they will cancel out from each other, and I will get an expression which is this. Now Ec minus Ev is nothing but Eg, if you remember. This is Ec, this is Ev. Ec minus Ev, if you find out, this is your Eg. So I get minus Eg by kT. So I get Ni square equals to NCNV exponential minus Eg by kT, where Eg is the band gap between the two. And this gives you a relationship between Ni and Eg, right. So it makes sense also if you look very carefully at the Eg becomes large, since it is exponentially negative, my Ni square drops down drastically, right. And similarly, if on the other side, if the Eg is small, I will get a relatively a much larger value of Ni. So two things take away again here, that Eg and Ni are related to each other, the band gap and the intrinsic carrier concentrations are related to each other. Also, if you look very carefully, Ni square has a dependency on T also, temperature, right. We do not talk about it in general semiconductor when we do it in our colleges and universities, because we are actually talking only of 300 Kelvin, right. So my temperature does not vary too much in standard scenarios. But when we talk of cryogenics, the same temperature T, which was initially 300 Kelvin, falls down to, let us say 0.4, 0.5, 4 Kelvin or so on and so forth. Even if you do not understand the first two slides, even therefore if you see, as the temperature falls down, this quantity becomes negatively more large, and therefore this quantity exponentially falls down much lower, and therefore that is the reason you almost have no carriers available. Intrinsic carrier concentration is almost 0, right. So this is the basic relationship between Ni and Eg, the intrinsic carrier concentration and the band gap. Let us look at a numerical approach to consolidate what we are discussing now, right. So we are told to calculate the carrier concentration in silicon at T equals to 110 Kelvin, let us suppose, or maybe 100 Kelvin, does not matter. So if you use this relationship, I get Ni square equals to NCNV exponential minus Eg by kT. Now if you look at there's a model which I have already discussed earlier, known as Varshini model. Within this Varshini model, it relates the band gap at any temperature T with the band gap at Kelvin, at 0 Kelvin, and then and it depends upon capital T, right. So this is, we refer to as Eg0, given by this quantity. Alpha, beta are known to you, you can get it from standard text. So if I calculate the Eg value, I get 1.1487, right. This is known to you, these are all standard values available to us. T is 110 Kelvin, I put the value here and I plug the value of all these constants and I get the value of Egt as 1.1487, right. And as you can see, therefore, the Varshini model predicted it in a semi-empirical fashion, but even physically if you look, Eg0, right, Eg0 is 1.169, right, and Eg at 110 is approximately 1.148 or 9 maybe, right, EV, it is fallen down. So there's a decrease or decrement in the value of your band gap, right. So just plug the value of Eg into that expression and you can get the value of Ni square. Now how to calculate NCNV? NCNV is quite a complicated equation, you can get it from your standard books available to you, and you can, NCNV depends upon the Boltzmann constant, the temperature, effective mass of electron and the Planck's constant here, right. Similarly, it depends upon the hole here and everything else remains same. So if I can plug the value of KBT, pi, MEHT at, we can find the value of NCNV at 110 Kelvin, right. If I get the value and I plug these values of Nc, Nv in that which expression, the previous expression which was there, this expression, and we plug the value of Eg, this one, in this expression, take T equals to 110 Kelvin, Boltzmann constant is already known to us, I get the value of Ni to be equals to this much. That is what you see. Numerically even is being confirmed that the intrinsic carrier falls down to 10 to the power minus 8, whereas at room temperature this was approximately 10 to the power 10. So, effectively 18 order decrement in the intrinsic carrier concentration takes as you move your temperature from 300 Kelvin to approximately 110 Kelvin, right. And that is the cost you pay for working at a much lower temperature, that your intrinsic carrier concentrations are very, very small. I had shown you for 110. So, let us look at two more temperatures, one at T equals to 250 Kelvin and the other at T equals to 400 Kelvin, right. And now in this case for 300 Kelvin Nc Nv has been given to you, right. We all know that Nc Nv, I mean you might not be knowing at this stage, but standard one in devices, that Nc Nv varies as T to the power 3 by 2, right. So, the number of states, right, per unit volume, per unit energy state. The band gap energy of the silicon is given as 1.12 eV, and assuming that it does not vary with temperature, we find out that Ni square equals to Nc Nv exponential minus Eg by kT. Therefore, I get this much amount of Ni, and it is a known quantity. I hope you all know this quantity very well. In a much easier fashion you can handle Ni square, and this becomes Ni at this is at 250 Kelvin. At 250 Kelvin I get 7. So, if you look at 300 to 250, which is about 50 Kelvin drop, I went from 10 to the power 10 to 10 to the power 7, 3 orders of decrement in the value of Ni. Now, if you look at 400 Kelvin, I get 2.38 into 10 to the power 12 centimeter cube, which means that there is 2 order increase. So, with respect to 300 Kelvin, as you move your temperature up, my intrinsic carrier concentration goes up, as you go down it goes down, right. At 4 Kelvin almost 0 intrinsic carrier concentration to a very large value. So, this is what I want to underline or explain to you about this part of it, where Ni dependency on both Eg and the carrier concentration is known to you, right. So, what we learn now is that as your temperature increases, you see that this becomes 2 orders of increase. So, there is an order of increase. If you look at order, it is 2 times order increment, whereas if you go to 250 Kelvin there is a decrement of 3 orders, right. And that is the takeaway of all this lecture, at least, that I have been able to tell you that these two important things are there. Now, let me therefore recapitulate what we learned in this lecture series, at least in this lecture 1. We learned 2 things, that the total number of intrinsic carrier concentration is multiplication of the Fermi probability distribution function and the energy states distribution function. We also found out that basically the area under the curve is basically the number of Ni which is available to you, or intrinsic carrier concentration available to you. As you lower the temperature, the area almost goes down to 0. There is reduction in the value of Ni as temperature comes down, and this is drastic at a low temperature, somewhere around 10 to 4.2 Kelvin. So, when you talk of cryogenic temperatures, the cost we are paying for working at cryogenic is that your intrinsic carrier concentrations are very, very low. The last thing which we came to now, that we gave a numerical example to showcase that the low temperature change with respect to Ni. So, I hope you have understood this lecture and you enjoyed it. We will discuss other factors of cryogenics in the next lecture. Thank you.